morning. Okay, I think we may start. I know this is the lowest attended class today. Hopefully there will be people coming in. And I don't know whether we said you please try to catch up with those MATLAB code. So I just want to ask you, have anybody tried to push through what has been asked to do? Because we have a tutorial today. So I just want to make sure the assignment 1 part is completed. Okay. Yeah. I think, okay. So how about the other people here? First two completed. And 2.5, how about 2.5? No. Okay, because that's what I wanted to. I think it's a good idea to, see what's going on, Yeah. So, but the problem number 2, you think it's controllable and observable or controllable? Did you check that out? I think you need to check that out. There are zeros in one of those columns. Try to check it out. Okay. Okay. Yeah, you need to AC and BC, you're calculating using A and B. That is correct. But remember, you're doing that, but in real practice, you only see AZK, BZK. You don't see A and B. Only for the purpose of control design and for testing or verification, we are doing you're computing AZK, BZK. Remember that. So when I'm trying to control a process with the network control system, for me it appears like AZK, BZK, with AZK and BZK unknown. Yeah. Right. So it does work. Right. And the reason that those are is just to show how we can transform a system with a network in the loop into a linear network control system. That's basically it. And even if you transform it, even though you have A and B known precisely, what we are claiming is the AZK, BZK is still unknown. Remember that. That's another reason. Why? Because the delays and packet losses are not precisely known. You see, you understand, right? Even if you know A and B precisely, and when you bring that network inside that feedback loop, you would have a AZK, BZK, whose values are not known because the network delays are unknown. It's random. Yeah, that is correct. So when A and B are unknown, definitely everything is unknown. Whereas if you know A and B, even then, AZK, BZK, the dynamics are unknown. And the reason is unknown is because of the network, which is a random variable. Yeah, you only know the distribution you might have seen, but not the precise values. And that changes the AZK and BZK because you won't know. Okay? All right, any other questions, guys? I know some of you came a few minutes here. So I was asking if you guys have completed your assignment 1. Because now today afternoon, we're going to move on with assignment 2. That's why I was asking. How many of you how far are you guys? You have done 2. How about 2.5? Okay, 2.5 is what they said they had some issue. I was asking them to check the controllability in general, But if it is controllable, we are able to do it, then there is some other issue. Yeah. The dimensions, like you said, yeah. Ah, check. Yeah, dimensions, so you have to check. Okay, okay. Okay, I think, yeah, please do check that. I think those are important, I think, as part of this. See, this is one reason why we can do everything within one day, right? You know, because we got stuff going on. If it's a semester long, you have a little more time. Yeah. But you can figure it out, even though, you know, you saw it should work. There's no difference. Yeah, sometime, yeah. All right, guys, how about you guys at the back? Two problems I was asking, right? 2.5. Anybody do 2.5? At least they are far ahead. They say that 2.5, other than 2.5, everything else is working. How about you guys? Any experience? You have not gone there. But how about 2.2 or 2.3? 2.2? Yeah. All right. So I think try to do this. It would make it easier. So today, you know, I keep moving. So that's why I was asking you. So now we are going to go into nonlinear network control system. So far we did linear. Now we would take a system that's nonlinear, and the question was, it's the same process. How do you come up with a FZK and GZK? Very similar with the packet losses and delays, right? It's the same integral, so there's no difference in there. But I'm just saying, and then we want to use, since it's nonlinear, we have to use a neural network. Okay? So this is lectures 7 and 8, so hopefully we can do 7 today. All right? So if you look at this system, here you see there is the continuous time plant, which is nonlinear. You have a state quantizer. Okay? So let's assume that you don't have state quantizer for now. And you have a delay in packet losses. Let's assume that. And you have a discrete controller. And normally you have another quantizer. And then that goes through the network. And then you get the actuator receives the quantized control input. This is typically what it is. Okay? So initially we can remove these quantizers and just use only delays and packet losses because we know how to handle that, the quantizer. So very similar to our linear, we still have the same block diagram here. So when you send a sensor input, it takes so many seconds delay through the network, and from there, from the controller receives that, and from there it takes another a few seconds. We call this whole time called round trip delay. It's a round trip delay, okay? So this is what they talk about in networks. It's called RTT. That is basically this whole thing. It's a round trip. It's a closed loop, kind of closed loop delay. So that delay, and ultimately you see that it reaches the actuator. So there is a little bit of a delay there, and that delay varies because of randomness in the network. You see? So we assume that it has a bound, but ultimately sometimes you may not. So the network can hang up and things may not be flowing through the network. Right? Remember that sometimes you have a congestion and you have to really turn it on and turn it off, basically. Okay? So you can see that top line sensor packet sent, middle line controller receiving the sensor packet, computes the control input and then transmits it, and then bottom line is the actuator receives control action. Okay? So there are some assumptions you need. One is the sensor is time driven. So that means that the sensor is basically measuring the state vector with respect to time. Communication network is a wide area network, so that the network induced delays are independent and unknown, whereas the probability distribution functions are considered known. So what it means independent is, you see that the same network you are using for sensor to controller and controller to the actuator. So for the sake of analysis, we assume that these values have nothing to do with these values. So it has enough bandwidth that these two sites are independent. That's the assumption there. Okay? And you only know probability distribution. This is what I was telling you. You don't know precisely the delays and packet losses. That's why the dynamics becomes unknown. Even though the original system, like you guys were looking at linear system, even if A and B matrices are known precisely, the minute you bring in the network and it becomes AZK, BZK, immediately we say that it's unknown. And that's the reason. And I showed you some simulations where if you know A and B and you design a controller, but you have the network, it blows up. There are some examples I showed you where it blows up because of network delays and packet losses. And that's the reason why it blows up. You see? All right? And the third assumption is the sum of network-induced delay and quantization delay is bounded, while the initial state is deterministic. So always we assume the initial state to be deterministic. This is very difficult. Okay? And the sum of the delays, all the delays, we assume it's bounded because otherwise it runs open loop really and then you cannot control it. Remember we talked about what happens if it's over a sampling interval. Then you are running open loop, and as I said, so with event triggering, many times we extend the sampling. But initially, when you don't know the system dynamics, mathematically what we have shown, although I'm not going to cover this, you have to sample more often. Why? Why? You understand what my question is? Okay. So one thing we said, the sampling interval, like the delays, has to be less than a sampling interval or something close enough. But we can still handle when the delays are over a sampling interval. That means when it goes more than a sampling interval, the system is running open loop. Make sense? Everybody understands that? Okay. So my question now is, let's say there is event triggered paradigm, okay, where we stretch the sampling interval. Okay? So the question was, if the delays are more than a sampling interval, okay, assume that, and you don't know the dynamics of the system. You don't know the dynamics of the system. Why extending the sampling interval would fail? It's even with adaptive control this happens, or learning-based control, this happens. Why does it fail? Right? But that can happen even with known dynamics too, right? Even if A and B are known, let's say you stretch the sampling interval. Let's assume that, okay? Don't worry about the losses, whatever. Even if you know the A and B, let's say you stretch the timing sampling, that means the system is running open loop, right? And it can become unstable because it's not closed. But my question is, if A and B is unknown, for example, why is it even more important to sample more often? Do you understand that question? Okay, so you see what I'm saying? So let's say that if you know the dynamics A and B, you're stretching the sampling interval. So that means you're running the system open loop, okay, right? So it so happens that you don't get the feedback on time. Sometimes it could become unstable because there's a margin of stability, and so forth. But this is even more severe when the dynamics are unknown rather than the dynamics are known. Why? And what happens when the dynamics are unknown, when you're, we have seen all these controllers. You guys have ran the Q-learning controller. Why is that important that you got to make sure that there is enough samples? Why? I don't know, most of you never asked this question. This is very important. This is part of the learning stuff. One is to run the code and show some plots, right? The other one is what is happening here. So why is that? When the system dynamics are unknown, it's even more important to do the sampling. But she has a hint there, and we have to use her hint. Now, let me help you. So let's say you're trying to learn, okay? What do? Let's say the controller has to learn something. So what does the controller need? Data. That's right. That's right. So when ACK and BCK are present, and the dynamics are unknown, the first few seconds, the controller is trying to learn and understand the dynamics. That's what is happening in all these controllers. Right. That's why, since the error is more, it's trying to understand and tries to quench the error. So the first few samples are extremely important. Now, so when in the point of learning, when you're stretching that time, that means you're not getting enough information from the system. So the controller is unable to learn, and it can cause the system quickly unstable. So remember that. So as you're learning, it's like practice. You've got to have some information coming through. Then only you know whether what you're doing is correct or not. So in the steady state mode, that's okay. So if you remember when I did the event trigger control papers, what happened is when we were doing that using neural networks, always the sampling interval will be equal to the event triggered sampling interval will be equal to the regular sampling interval initially. This is just adaptive. And after that, once the dynamics are learned, it starts stretching. The same. So this is very critical. Yeah, you can see that very nicely in that the way the mathematics works.
In the unknown, hidden dynamics, faster dynamics can be.
It has to be stable. There's no doubt. And the same thing, right? You know, in order to stabilize it, let's say even if it's stable, in order to stabilize it, and it's unknown, so you got to get that information so that your controller is trying to tune those gains, whatever.
Initially, the sampling will be dense.
Right, exactly. After that, you can start stretching. Yeah. So if you look at many of my papers, that's how it looks like. Yeah. So maybe if I cover, I'll show you if I have anything on that slide. But yeah. But that's what it is. So the reason why it happens is because the controller is naturally trying to learn the dynamics initially, and that's why you have more samples. You can't go any smaller than a sampling interval. So therefore, that time, that event triggered sampling is equal to the regular periodic sampling. And once it learns, then you will see that it stretches the event triggered sampling. So keep that in mind. Okay, so that learning part in there. So that's why I think it's also equally important that you really don't want to have the delays, some of the delays even more, primarily because then you're running the system open loop. And the controller is unable to what is it doing? It's basically probing and through the data and trying to understand what the dynamics are so that it tries to learn from it. So now it's not there if you stretch the time. You see? And this happens even for human. Right? If you imagine you have to go to a lab, you have to do some tests. Let's say that lab is closed whenever you're coming in, what will happen? What will happen? Yeah, you're not getting access to it, and so you try it for 10 times, 20 times. After that, you get fed up and say, well, this lab is closed always, and I hell with it. So the same thing. Yeah. So you have to have some data. that needs. So that's important. But either way, this is a very critical assumption. So the total delay has to be bounded, but it has to be reasonable. And that value depends on the practical system. It's not the same. So some systems are slow. Maybe you can handle longer, but some systems are very fast. Then you may have to have a faster sampling interval. Okay? All right. So this part we talked a bit about it, like linear network control systems, known dynamics. That's what people have done in 1988, and you can see that. Then optimal control for linear NCS with known system dynamics was also done in 2002 and all that. But it's all known dynamics basically. And stable control of nonlinear network control systems with known system dynamics was also done in 2001 and 2003. But what we are dealing with is, well, can we do optimal control for nonlinear network control systems with unknown dynamics? I think that's basically what we are all interested. And can we do that some way, like using an adaptation, right? Learning an adaptation. And that's basically what we are trying to do. And it's a nonlinear. In the linear case, we use Q-learning. In the nonlinear case, we already learned neural network stuff. We are going to apply here. So basically, we are going to use neural networks. And since we are using neural networks and dynamic programming, remember that Bellman equation? Basically, we call that as neurodynamic programming. And so it has very similar relationship with reinforcement learning because you get the Bellman equation and all that. And use that temporal difference error, therefore that's basically how we claim it's a reinforcement learning. Okay? So wireless imperfections can cause significant challenges which are considered here. So you see that originally we start with the same thing that we did, a nonlinear system in continuous time. Just like we did in the linear system case, you integrate it, and the book has a little more details. So if you integrate it, you do like what you did, kt to tau d minus dt, very similar like what you just said. And you end up in getting, there are two different ways you can write this system. One is you can have a z of k. The z of k, you can write it as a state and previous values of the control input, or you can take the output and you can mention output and then previous control inputs. So you can have your dynamics can be expressed either using measured state value like here or using measured output. In either way, you end up in getting a form of equation like this, which is z of k plus 1 is h times z of k plus l times this, times u, y is equal to c naught. So, just like a linear system, this becomes discrete time, h and l are become unknown. Okay? So, h and l becomes unknown. The uncertainty is coming in because of delays and packet loss. Very similar. Okay? So the same thing you can do. Let's say if C is convertible or invertible in this case, then you can write this dynamics. Okay, and this, you can write it in the form of what we call input-output data. Somebody was asking me this. So you can write it as input-output rather than state. So if you do that, you can actually come up with another equation like this in terms of y of k plus 1. Then you can write that y of k plus 1 is f and g, and this f and g basically are functions of the outputs. See the yk naught is basically defined as the current value of the output and the previous values of the input. So you can actually transform that system either using the outputs or using the states. You see what I'm saying? So only you need to remember is what is your augmented vector that you're going to do. Does it have the output or does it have the state vector? Any questions here? So the design is the same. No matter whether you do the input-output form, equation 3, or you do use equation 2, the design is same. So I'm not going to give you the difference. You know what I mean? So typical, it's very typical that y is measured. But there are a lot of places you look at when what happens when X is measured. Okay, what's your question? Here we don't use the observer because you are converting the system into input-output form. So what the good thing with this is you don't need the observer, but you still need an identifier because the F and G is unknown. So now you are building the F and G using the outputs. Exactly. So we don't need an observer, but you need an identifier. Got it? So you see the difference, right? An observer sometimes can be identifier, sometimes is not. And that's the difference. Yeah. Okay, any other questions? I see some new faces at the back. So you are new faces? Yeah. You see? So what's going on? You didn't come all these few classes? Okay. But I think there's a sign sheet, I think, right? Yeah. Okay, so I know the people who are on the left side, and except one or two people, they have been periodically coming. And this side is mainly those people who come and go, like a random. Yeah, all right. Okay, so is that clear now, right? There are two systems, but I'm not going to go through each of them. It's basically the approach is the same. Okay? So in one case, you are using the state, x of k. In the other case, you are using the measured output, but the ideas are all the same. Got it? Okay. So now, since it's nonlinear and unknown, we use the same ideas of dynamic programming and the reinforcement learning. So what we are going to do is we're going to define a value function or a cost function. Let's assume you're doing with respect to the state. So it's the expected value of this, okay? And you see that this is quantized input here, okay? And then on the other system, you replace the Zi with the output vector. Remember that we defined. So it's the same thing, okay? And this has got the infinite horizon. And here in Qy is C naught inverse Qz C naught, Ry is Rz. So same thing, you know. So now, let's go back and look at the traditional optimal control, just to recap. So if I have a nonlinear system, and if I don't have the network delays and packet losses, let's say FD and ZD are nonlinear. Okay? So the way you come up with the optimal control is you first form the Bellman equation, right? The recursive equation. And it has this is a finite horizon, n minus 1. So there is a terminal constraint. There's a second equation. Okay? And then what do you do? This is n minus 1. This is up to n minus 1. K going from 0 to 1 up to n minus 1. And this is n. K equal to n here. Okay? So then what you do is you write this in the form of Bellman equation, a recursive equation. So remember we said k to n minus n is equal to k to k plus 1 and k plus 1 to n. Recursive equation. Okay? Then to find the optimality, what do? You basically move that left-hand side to the right-hand side and take the partial with respect to UDK, because we are trying to find the optimal control input. So you take that partial with respect to UDK. So here is the UDK. So if you do that, then you get this expression. And then from there you are getting the optimal control input. Okay? So the optimal control input is R inverse. It requires the G matrix or G vector, whatever. And then it takes the partial V star over future value of the state. So this derivative, we don't have it. And if G is unknown, we also don't have it. So when we don't have the dynamics, we have to use two neural networks. Remember that. Or you have to use an identifier. Okay? So that's number one. We already have seen how to tune this. Because remember we saw that last class, we used to tune the critique, we use what error to tune the critique? So we need two error terms. One is to tune the critique, the other one is to tune what? The actor. So the critique is tuned by using Bellman error, exactly. Don't forget that. And if there is a terminal constraint there, you also get the terminal constraint error and you sum them up and you use that to tune that. Remember that? So, but then to tune the actor, what error do we use? To tune the actor, we call it as a control input error. Control input error. So that basically the same thing that we are going to apply here also. Okay? So we are going to do the cost function and then we are going to define the control input and we are going to do the same. So that's why I think we have that reinforcement learning I gave you without all this network control, the same idea. The only difference is we are dealing this with expected value. There we don't have to put the expected. That's the difference. Okay? So in this case, that's what we do. And you plug this optimal control input back into this, you get the HJB equation. So this equation is the HJB equation. And the HJB equation, like we talked about it, it's a function of the dynamics and it's unknown. There's no closed form solution. So you have to either solve it offline, numerically. In this case, what we are doing is we are trying to solve it in real time. Okay, so now we try to do that with network in there. So now, see, I don't have quantization. So I have a network. So I have these delays and packet losses. So I'm taking this continuous dynamics. I follow the same process here. And then I get a discrete dynamics. Okay. So you see that f of zk, g of zk. So f and z are unknown, right? So now we will use an identifier, first step. So the identifier, the purpose of the identifier is to estimate f and g. Okay? So the same approach that we used, you write the dynamics, you see that one big neural network. WF and WG are two parts. One for approximate F, the other one to approximate G. And we are combining into one neural network, okay? And by doing that, we also get this 1 and UK minus 1, that becomes capital UK minus 1 here. So we make that as a vector, and we are basically combining these two matrices into one matrix, and then we are tuning it just for simplicity. It works. Okay? And so then what we do is we are trying to find the actual weights, which is approximated by the neural network. And so this is the identification error, z minus z hat. Z is measured, z hat. And so now you're using the history. Now why do we need the history? I already told you. Why are we using the history? Because if you look at that error, the 6.16, it uses the history rather than individual values at every instant of time. Why? Why do you need to construct a history so that we get the same error equation in terms of history? You see that zk minus 1, zk plus 1 minus L. So it's like an history. So 6.16. Why do we need the history equation? I said that. I did explain to you why you need that. Huh? To persistently excite him. See? I'm happy you are reading the material. That's right. And why do we need persistence of excitation? Why do we care? To identify, right? So that means, remember I said you have a black box, you are trying to feed some inputs, and you're trying to understand which inputs are going to excite what is in there. When I say excite, it's going to, if you have a resistor, inductor, and a capacitor, it's going to create such input so that you know, as when you measure the output, you know this behaves like a capacitor inside. This looks like an inductor inside that. That's what it's doing. So persistency of excitation condition is very important. And at one value, it doesn't satisfy. You have to use the history, and it becomes a matrix. And we show that that matrix is invertible. If it's invertible with those inputs that you are feeding, the signals, then we claim that it is persistently excited. Unless it happens, the identifier will not be able to capture what is F and what is G. Remember that. Okay? So the persistency of excitation is a condition that's usually needed for identification, and that's basically in the adaptive control. Now, in the 2010 work, if you remember, I gave the paper. So there is a guy, Girish Chowdhury, he came up with the data, using data, they call that as a concurrent learning. So instead of doing this, because the condition is so hard, they use the data, which is very similar to what we are doing, but we never call concurrent learning. But that data he used, and he was building a matrix as you controlling the system, and then he's creating that PE condition. It's a really nice paper. Yeah. So with data, you could create that. Okay? And that's what we are doing here. So with data, we are able to create it, and then we use this equation rather than that, basically, for our analysis. Okay? For our analysis, that equation is being used. So then the steps are very similar. So basically, you take that equation and you do the analysis. So all these steps are pretty much in the intermediate steps, and this one. Here is the update law. Remember, this update law is the least squares. Least squares update law. It takes that error equation and takes the gradient, and you end up in getting that. And when you plug this equation, you end up in a exponentially stable. This alpha I is a positive quantity, so this system is exponentially stable. That means that the identification error converges. Okay, this is the ideal case. And this is a very good thing about that, how we came up with that update law. And you see that the PE condition is needed here in order to show that this matrix is invertible. That's what we need, the PE condition. So if you don't use that history, that matrix will not be invertible. Any questions? So this part is very similar to what we have shown before. So nothing new about it. Any questions, guys? Okay. So now you see that because this is expected stuff, we prove that it is bounded in the mean, boundedness in the mean. Otherwise, we just show boundedness. So here we show that this is expected of this boundedness, so therefore we call that as a boundedness in the mean for the neural network identifier. So here you show the learning rate has to be selected between 0, greater than 0, and some value which is upper bounded. And then the weight estimation error are all bounded in the mean with the fixed final time 0, comma NPS. NPS is the final time. Okay? Then you try to approximate the stochastic value function. So now we got the identification. The identifier would give you F hat and G hat, right? So now we are doing the value function. So value function also you use a neural network. You see that neural network here? And you see that there is n minus k. That's the time varying basis function. And I already explained to you, since this is a finite time, we are talking about compact sets, you are still okay to approximate. Okay, because the time is finite. Alright? And here is the actual value of the V hat. The value function V hat is the output of the neural network. W hat V, K, and then here is the basis function. So the main challenge is this basis function. So how do you come up with a basis function in order for the controller to converge? So there's a lot of time we spent on that. So we did include also a saturation when we did the simulation. And what is the purpose of the saturation? To make sure that the values are bounded. Because for neural network approximation, the activation functions have to be bounded. Okay? So we had that issue of the time. And we're doing a polynomial because a single layer network, it has to form a basis. So we have to do a saturation in there. Okay? So then you get the Bellman equation here. Okay, that's the Bellman error. You can see that, that's the Bellman error. Once you get the Bellman error, then we basically find the update law for the Bellman equation. So you see that how it looks complicated now? In fact, the procedure is identical to what we did last few classes for nonlinear systems. But here, because of the expected value, it becomes really complicated. So you have two errors. One is the HJB error, and the other error is the terminal constraint error. So the terminal constraint error is this here. And the HJB error is here. So you have two errors, and we have to come up with an update law using those two errors so that you are adjusting those weights of the neural network. Okay? So here is the update law. Now look at this update law. This update law uses the previous value plus alpha v times this term. This is the average effect, right? This is 1 plus z. So this is a basis. This value is always less than 1. Now why is this always less than 1? Why is it always less than 1? Now, look at that equation. So let's say I have like so if I have an equation like this, a over a square plus 1 is always less than 1. Make sense? Everybody agrees or no? Is it true or not? So here, instead of a, this is a psi of this divided by psi transpose psi, which is plus 1. So that's the same thing. So this term is always less than 1. Then you are multiplying by the terminal constraint error. Here you are multiplying by the HJB error. But you see that this is more like an averaging. So there are some people in nonlinear control, which is true. These type of update laws, if you take a nonlinear control, they slow down the learning process. But we are using it because if you don't use it, it's very difficult to show stability. So by doing this type of thing, in adaptive control, the nonlinear guys, Christie and others, they have shown that it takes basically a lot longer. Sometimes it may even become unstable. In this case, you have to use that kind of a update law. So this is the update law we use for tuning the critique weights. This is the actor. This is the actor design. Okay. So you are now designing the actor which generates the optimal control input. So you use remember we said there are two ways you compute the optimal control and then you subtract one from the other, and we call that as a control input error. Okay? You get the control input error and then you come up with an update law for the actor. So you have an update law for the critique, you have an update law for the actor. So we are using two neural networks plus the third neural network for the third neural network is used for what? For identifying. We are using three neural networks here. So here is the flow chart. Okay. So the flow chart basically starts with what we just did. You initialize the value function and the control input has to be initial admissible control. Remember that? We talked about it. Then you first update the identifier weights. And then you update the critique weights and value function. Then you update the actor weights and control policy. You check whether the time is equal to final time. If it's not, then you update the time and you go back. Otherwise, you reach the final time and you stop. So this is how the simulation code is written. MATLAB. Any questions here? So the critique, adaptive critique design is the same, whether you are using a network or not a network. The reason we use expected value here is primarily because the system becomes stochastic. And f and g, just like we saw in the linear case, f and g becomes a function of random delays and packet losses. See? Okay, any questions, guys? Yeah. You may have to raise your voice because of the fan. That is correct. You take the same measured states. Like the vector, augmented vector, remember? That's all you're doing. That's right. You use those augmented vectors. Okay? And that's all the things you are measuring, right? Only thing is you are combining, the reason I said augmented because you are adding those history. That's right. Any other questions? And it's the same, whether it's a stochastic or a deterministic case. It's the same idea. The only thing in stochastic is you bring that expected value. Since his expected value, you see that under E, we put that delay and packet loss. Because it's basically you're taking the expected value because of those two quantities which are random. And that's the notation normally we use. Okay? Any other questions, guys? Any other questions? So the design shouldn't be confused, right? It's the same. Even without randomness, right? It's the same design. So we are applying now the same design now in this. And remember I told you the control input error and the Bellman error was a challenge for us because how do you tune those weights? And you can't use the same Bellman error for both and you try using it, it doesn't work. So that was a challenge. Okay? Alright. So here is a fancy controller block diagram. Alright, all different colors and even a little bit of shading in there. So you can see there are two cases here. One is you see that there is an identifier. Okay? So there is an identifier and then you see that here is the identifier history stuff that we talked about and it generates f hat, it generates g hat. And then it's using that g hat into the actor network. You can do any number of ways. And then you have the terminal constraint error, you have the Bellman error. These are used to update the critique neural network weights. Okay, and here we are using that g hat information to compute the u hat. And you're using the u hat. And you can see that this is a neural network, two-layer neural network. With first layer, neural network weights are selected at random and basically frozen. So for a basis function, it's very difficult to select. So somebody basically, Pao, he does pattern recognition. He came up with the idea that you pick the input to hidden layer weights and you select it at random and you freeze it and only you tune the output layer weights, then that particular way of doing it becomes still one layer of neural network and input to hidden layer weights form a basis. So we use that idea here and we are only tuning one layer of weights. Okay? So this is the block diagram for the controller. And you can do that for the different system, and this is a different, the similar idea, but a different system here. So it's a very similar idea, but the inputs, in one case you're using state vector, in the other case you're using the output vector. Okay, so here is the overall stochastic optimality theorem, convergence of the stochastic optimal control input. And you can see that there is a bounds on these learning rates for the critique, learning rates for the actor, all that stuff. It has to satisfy those conditions. Then we claim that all the closed loop signals are bounded. And the bounds depend on the final time instant, initial state bound, identification error bound, and the weighted, these are very critical, and they're all bounded in the mean. They're all bounded in the mean. Okay? So this is kind of a theorem that pulls in all the stability. So here is a table. Okay, it's like a flow chart. I'll skip this. So let's take an example. So let's say you guys are familiar with this tooling robot now, right? So here is a tooling robot in continuous time dynamics, where f of x is given by that. So dy dt of x1 dot equal to x3, do dt of x2 dot equal to x4. So rate of change of position is, angular position is velocity for the toolings. That's what that is. And then the do dt of the x2 dot and x4 dot basically becomes that dynamics there. So this is f of x, and this is g of x. Okay? So this is f of x and this is g of x. Alright? So here we are selecting the network parameters. Sampling time 10 milliseconds, upper bound on the network induced delay is 20 milliseconds. So here is greater than the sampling interval. You see? Got it? Okay. So network induced delays, the sensor to controller here. So sensor to controller delay is about 8 milliseconds, and the other delay is about 15 milliseconds. And network induced packet losses follow the Bernoulli distribution with gamma bar equal to 0.3. So you look at the Bernoulli distribution, and MATLAB has a little command. You provide the gamma bar value and it generates that. And actually I have a plot, I think. So here is the delays and packet losses. So you see that the packets are getting dropped, and you see 1 and 0, 1 and 0. 0 denotes packet is lost. You see? Okay? And that's random. So you see that it's not really periodic. So you see a drop here, you see a drop, next you see a drop here. So it's not periodic. You understand that? That's a random. I want to make sure you understand. So here is the sensor to controller delay with respect to time, and here is the controller to the actuator delay. That's also with respect to time. Okay. So we have that, and we put the total time. In this case is about 2000. Final time is 2000, and we repeated for the sake of ergodic behavior 1000 iterations. So one of the questions I asked you was for you to check what is ergodic behavior. Anybody check that? So what was the meaning? You need to speak louder. Because of the fan, they can't hear you. Right. So time average is typical with the regular deterministic. Here we are doing ensemble, that is taking many, and then you are averaging it out. That's why we do that. Ergodic behavior, so it will make sure it's safe. Okay? I think any questions there? Do you guys understand what she said? Okay. And you are nice to her. Is that why you are nodding? You really understand? All right. Okay, any other questions here? Any other questions? So this is what is happening, right? Then the other things you need to determine. One is you see that the augmented vector. Here I am selecting x of k just for sake of argument. I only pick two former values of u. Okay, so it is a 3 by 1 vector, right? And here is the initial admissible control. Okay, this is my initial admissible control. Here is my initial state vector. It's a deterministic. Remember, initial state vector has to be deterministic. Initial admissible control. So remember, we talked about the difference between stabilizing control and admissible control. So, and there's always a debate. How do you pick that value when you don't know the dynamics? So this is always a challenge. And we try to relax it. We did that, but really mathematically it becomes really bloody in the proofs and all. And it does work, but it becomes really complicated. Okay? So now what we are trying to do is we want to see if the controller works. So you can see here from this plot, all the regulation errors, they converge without 8 seconds. So here are the learning rates. Okay, so with this, it converges pretty nicely. The control input also converges very quickly. So that means that even though the dynamics is unknown to the controller, the neural network is able to learn pretty quickly, even in the stochastic domain, and is able to do a good job, right? Even though the delays and packet losses are random. You see that? So that seems to work pretty nice. So now I'm trying to use a feedback linearizing controller. So the feedback linearizing controller, basically I'm assuming that in this case that the dynamics are not at one instant of time. I'm designing a feedback linearizing controller. But remember, the delays and packet losses are changing. Because it changes, a feedback linearization controller cannot keep the system stable. F and G is known, but it's changing because of the delay and packet losses. So if you take the average value and you assume you know that, and you design a feedback linearizing controller, it blows up. Because the values are changing.
It is not cancel the nonlinear.
Exactly, it's not able to cancel precisely nonlinear dynamics. Got it? Okay. And with our controller, just like we talked about it, you see the critique weights are bounded, the actor weights are bounded, and then we show that the identification errors, remember I keep saying that, we have to show that, so we show that the identification errors also converge, and so you can see that by about 8 seconds it's converging. Because it converges, you can see that nicely these things will converge at about 8 seconds. So the identification error is the most important part. Okay? So they all converge very quickly as the consequence converges, and you can see that the HAB error and the terminal constraint error also converges. Nice. Now let's say that for the sake of argument I want to compare. So there are 3 different methods here. One is the proposed NDP based optimal control, which is blue in the middle. The red is ideal traditional offline optimal control, which is the red, which is the bottom. And then the green is feedback linearization control. Look at the cost. So the optimal control that we developed is in the middle. So what is the offline based optimal control? So what is the offline based optimal control? Why is it showing a lower cost than one that I explained to you? What is the difference? So in the offline based optimal control, remember I told you the value polish iteration method where you're holding the time and you're doing the iterations. So the good thing with that is the V hat will become V star at every sampling instant. So the method that you guys are doing or learning from me, basically we only do once a sampling instant, we are not doing the iterations. So V hat is not V star at each in a sampling interval. So there is an error in the, and that's why this controller is a little bit more expensive. than if you're running it offline by using policy and value iteration. You see what I'm saying? So why? Because when you do that, usually if you look at our old notes, you flip it, we usually hold that state and then we do many iterations so that you make sure that it converges before you move to the next step. That's what we are not doing here. Because why are we not doing? Because time. There's only so much of time for the sampling interval. You can do that many iterations within the sampling interval. So in about 2015, we came up with a method called hybrid, where we combine that iterations and also the time, and we shown that it's much better. But then the issue there was how to prove stability. So the good thing is we are able to show stability. So I can pick based on the sampling interval. I can, and the processor that I'm using, I can pick a few iterations to be executed within the sampling interval. Whereas the other methods, if you stop that iteration, it will lose up. You see? So that's what we did. We call that approach called hybrid. Hybrid is a combination between the iterative fixed finite number of iterations and the time used. Okay? And it works pretty nicely. So if you have a faster processor, you could actually add more number of iterations within the sampling interval. That means you're making that V-hat approach V-star at every instant of time. You see? Got it? So any questions here? So that's what the three different methods we contrasted, and you can clearly see that a feedback linearization method doesn't work, and so forth, okay? And it's more expensive. All right? Okay, so I'm going to stop here. I think there may be coffee, right? I think this is a good time. All right, guys. So I'm going to stop, and when we come back, I know we are going ahead, so that you guys can spend more time in the lab, and you can ask me questions, okay? So I think there is some coffee. Makes sense? I shouldn't want to tell you, but it's there. It's there. Okay. So you guys enjoy, and then come back with questions. Spend a few more minutes, but let me, before I move on. So I'm already did, I think, lecture 7. Lecture 8 is what I'm trying to do, so we're going a little bit more, but I wanted to ask you any questions you have based on what we... There was a question he asked me during the break. So one of the questions was, he was asking that, what if, you're selecting an initial admissible control. Is it possible that the agent can learn in a wrong way? Can it learn wrongly? What will happen? Any answers? You understand what I'm asking, right? His question was like, remember, we picked some value, we said we need initial admissible control and all that. So the question was, is it possible that the oral, basically because it has an oral agent there, which is control policy, actor and critic, can it learn in a wrong manner rather than you saw those results where nicely they converge? Right. That's right. That's right. But what is the guarantee? What is the guarantee that, I know that's what I'm showing you all those results, right? But what is the guarantee that the errors will converge? Why not the errors blow up? Still we see them crashing. Recently there are quite a few in US. We had some unfortunate things happening. So, yeah. So any other questions, guys, before we break for lunch? Yeah. You have to raise your voice a little bit. Yeah, value iteration, okay. It's the same method. Reinforcement learning is a framework. The value iteration and the policy iteration is how you solve those equations like the Bellman error equation and the control policy. So when you say value iteration or policy iteration, you are trying to solve those equations using iterative approach. That's all it is. It's still oral method, reinforcement method. That's what these guys do, machine learning people do. The CS people, computer science. You see? And that's an offline method. Whereas we have to use it for control, then you have to use what I was doing. We call that as time driven. Remember I gave you the code. Intro to oral, there are 2 codes. One is the value or policy iteration, the other code is for the time driven, without using policy or value iteration. I don't know how many of you run that code. The one that Dr. Bera gave, the intro to oral, there are 2 codes for 2 examples, right? 2 plans, yeah. So did anybody look at the code? I think I encourage you to look at it. I think everybody got that code, right? Yeah, I think I would rather run. So why don't you spend this time, before you come to the afternoon class, why don't you run it? So that has the value of policy iteration. The name iteration means you are solving those equations. The HJB equation or whatever by iteration. Okay? Any other questions, guys, before we break? All right, we are done. Nobody is raising their voice, so we stop it here. So we are early today by 15 minutes. To compensate those days we went past the 12 o'clock. So we will be here again at 2 o'clock, okay? The tutorial, okay? All right. Intro to RL code. So I know you guys are pretty sincere and you already gone through, but I'm asking about the people behind. Remember I said intro to RL. Huh? Did anybody run that intro to RL? There are two folders at least. One for value iteration and stuff, policy iteration. The other one is basically the time driven, actor-critic time driven with genome. Yeah, discrete time, because that's what we are trying to use there. So I want you to run it, feel it works, but I'm just saying that you see how it is being written and how the critique is being updated. I think it's very critical because all that concepts we are using in our slides. The only thing we do is we extended that to with an identifier, and so identifier relaxes the G also. Right. So it's important.
Good afternoon to all of you. So welcome to the assignment 2. We are going to solve, or we are going to discuss basically, and this is the tutorial 2 we are going to conduct. But let me tell you that as I have suggested that before going to do this assignment 2, once again you look into the basic program of RL once again, because that folder is already shared. So you just see that how the basic programming related to RL is working, okay? And now we will solve this assignment to be different way, what I thought. Till now you are following SAD's slides, okay? And today the problems related to the quantization basically we have. But have you looked any of the paper written by SAD? Then you will find that in paper in more details in simulation section you will find that the parameters are given. Okay, it is discussed in a more elaborately. So that's why you will find that today what I did, I'll come to this problem a little bit later, but just you see that one problem we have given in this way. You see the problem 3, you see what it is written, that consider the system given in 4 and 5. Basically here two systems are given, one discrete time LTN system which is a linear one, okay, and another is given continuous time dynamics of two-linked robot R. So these two systems is given, and now you see what in the problem 3 it is written, that is, consider the system given in 4 and 5, design a finite horizon optimal controller which is discussed in this particular paper, that is neural network based finite horizon optimal control of uncertain affine nonlinear discrete time systems. Okay, so I think I have already shared you know that particular paper. One second, another paper I want to show you that is related to quantization basically. This paper, have you seen? This paper particularly? You will find that this also sir has discussed, this one, that neural network based finite horizon optimal control of uncertain affine nonlinear discrete time systems. Okay. And someone is asking, you were asking that particularly how the parameters for that delay and this is actually given in the paper only. You will find that for the stability condition some bounds are there, and that bounds are declared there to establish the stability or guarantee the stability of the system. Okay. Once again, I will come to that. So here you will find that whatever the sir has discussed, everything is given more systematically. You can go through it such that you can understand. Okay. So this paper already I have shared. You just look into it, you open it and you see. Then I will come to the quantization part. You see, as the sir said, there is a Bellman error, then the total error, everything you will find here very clearly, and it is written very nicely, so you can follow it. And the way sir told that how you will find out the stability, the steps, everything is given clearly here. And more is that if you go to the simulation section, you see this is the bounds what we are talking about, 42, 43, 44 equation number. So you will find that exactly these bounds are also defined there at the beginning. So these are the two examples. Here it is there. Another is the tooling manipulator, what sir told. So these are the parameters. You will find that it is more details it is there, that what is the simulation time, what Q, R, all these values are chosen, what is the initial condition, what is the initial admissible control, that also it is mentioned clearly. Okay. So this paper you look into, I am showing you another thing very quickly. You go through it, then I will come to the original assignment. And have you went through little bit time, have you found to see the sir's book, what I have sent, book? That also you just open now. Then it will be easy for you to track what it is going and also to see the papers. That is very important to. So this is the chapter I am talking about, optimal control of unknown quantized network control system. This is the particular chapter I am talking about, 4, And the simulations we will do from this chapter only, chapter 4. Optimal control of unknown quantized network control system. This book you will find that the confirmation mail what I sent, with that the attachment is there. You just, if you have not downloaded, you download it and then you see. Little bit you go through it, then we will come to the problem. Just you see that what are the topics are already presented, you can correlate it with this particular chapter or not. So if you want to do this particular problem, if you want to handle this particular problem, you need to understand the quantizer also. So the equation related to quantizer you have to understand. So just you see this figure and see this equation, how you take some values, arbitrary values, and you match that whether you are able to correlate the quantization error or not. Then you will find that dynamic quantizer is also represented, that also you see. And mainly you see the flow charts also, then flow chart will be helpful to understand that particular programming also. Okay. So this is the paper also you can see, okay, that this finite horizon near optimal output feedback. Here actually output feedback what sir told, that means observer, this part. This is a particular paper where sir told about the output feedback, and also here one important thing. Can you remember the fact sir told that one important thing, whether you can remember it or not, that that non-quadratic functional we have used. What is the, can you tell what is the motivation behind it to use this particular non-quadratic functional in the cost function? Yes. Okay, so now let us come to the particular problem what we are going to deal with, and just I will tell you that many of you may be having some little bit of confusion that which folder, which particular program, this confusion is there. Let me tell you. You see, for the quantization we will take the same system, that is the batch reactor system, and we are going to that particular programming where it is actually in your case you will find that assignment 2 codes are there. Okay, here only you have to open this chapter 4.1. This is the, this is the one you have to open. Chapter 4.1. Okay, then you may be surprised to see that why these many other subroutines are there. If you see the main program, like now we have to use the actor critic, all this network. Actually inside program, this actor network, critic network, all these things are not. Even you will find that for the nonlinear case, the system is defined in a subroutine, okay, not in the main program. So whenever you will, like here you see action NN, then the activation vector. So all these are critic NN based argument, delay. Okay, so these are all H vector, H matrix. What the H matrix you have constructed, everything they have defined as a subroutine. So that's why when you will read the main program, you have to identify that what subroutine has been called. And your work is to see that subroutine, that what it is written inside. Then only you can correlate that whatever the actor network you have designed for that particular system, that is defined there. You have to see the steps. Then only you can understand. That's why I told you to see the book as well as the presentation as well as this particular programming. If you keep it side by side, you will find that everything you can identify at least. First you identify that which module is written for what. If you are able to identify that, in the next step you can build your logic, or you will try to find the logic that how the programming has been written. First step, you identify all the required subroutines to run that particular program. Like I'm coming to the programming 4.1, you see. So here these are the bounds actually which is defined as already I have shown in the. So you see here delay, they are doing the import data delay dot mat. So you will find that one MATLAB file they have generated, and from there actually the delay and the packet loss, that particular thing are imported. And this is known to you, that you see it is written already, that continuous time batch reactor system. Then you see here one function has been defined, myFun. In already you will find that it is defined as a functions there, and you have to identify that what is the need of that. And as I told you that if you want to discretize a continuous time system to the discrete one, then you need to have integration. So how you will do the integration, okay? That routine has been written and you have to identify that one, okay? Fine. Then you will find that this whole lot of exercise has been done to incorporated that delay and everything to find out that particular AZK and BZK matrices, okay? Fine. Now, and sir was also asking that how this H desired is calculated. So morning there and similar thing has been proposed for nonlinear system also, but here for the programming what we have provided, that is 4.2, it is not for the tooling manipulator. Okay, it is for this particular system. The 4.2 programming. This is the system for which the nonlinear system, the quantization based control, adaptive control has been proposed. and that you can look into, and if time permits, after understanding this, then you can change this nonlinear system to the tooling manipulator. Tooling manipulator is not there in the folder. Only you will find that batch reactor and the nonlinear system here. This one, these are the two things are there. Not the manipulator program is there. So manipulator program, if time permits today, but later on you can try it. But at least these two programming you see. First now I am telling that those who have not run the RL programming, that you run first, that you do. Then you come to this one. First you see the output of the RL program and you analyze that whether you are able to understand the basic RL based programming or not. Okay? Then we will come to this.
So in the RL program, they have written that some equation 23, equation 24 for the for the equation. But we can't make that which paper it is referred or which.
Yeah, that is 2012.
Sir said one paper.
It said that 2012 in the intro to NCS. Yeah, remember there is the Travis. So we can type.
You just tell me.
Explorer time-driven. Travis.
TR.
Yeah, time-driven. Let's see. Pulsar.
No, actually one paper I shared in the group. No, not this one. Earlier one paper I shared. No? Oh, 1 second.
That is the time-driven optimal control by Travis, and that's also when transactions on the network. They were just showing them in intro.
Okay, we can download that.
They have to download maybe time. I would say time-driven optimal control. And you said Travis and my name is TRAVIS. Tricks, EIERKS. Space.
Acha. KS only and Jagannath. This one? Here?
Let's see what that one is. Yeah. Maybe more than citation wise. Let's see. Yeah, that's it. This is it.
So I am posting this one in the group. You just see.
That's it. 2004. So this paper is the classical paper without any NCS. Okay? So I think you may want to look at it. This is just for the time-based, like what I just said, instead of value iteration. So that has a separate folder I gave you. Here we assume G is known. Remember we talked about it. F is unknown. Yeah, G is known, and you will see this is basic how you get the optimality.
So this is for the continuous value iteration.
That's a different one. This is the second folder, discrete time.
Main one.
Yeah. So take a look at that paper. Yeah, I will share it. The value iteration paper, I can share. Maybe I can find that and email you. You know. So you have that paper. The other one, the value iteration paper. Yeah, maybe I I can send you, maybe you would download this and we can share this one. This is the oral part. that's the paper, right? Which is
Yeah, that's why it is already mentioned. I'm searching for that. So, sir, why you have used the term that is time-based policy update?
It's like a traditional time-based means once a sampling instant, you're updating that multiple times, right? Yeah. That's what the value of policy. So next slide shows it works for when you have a large number of iterations, but if you don't use it, it goes up.
It will diverge.
There are two examples, right? One is the linear, other one is a non-linear system. No, it's just one data. The dimensions is based on how many neurons you select. So the number of neurons will dictate the dimension of the network, right? Just for normally you need to have many iterations, but here is just one. And your own, like how many, based on number of neurons you can change this. Oh yeah. And you know what you can do is, you can put some intermediate things and you want to see the plot, how the values how to change in the program, MATLAB, you can try to do that. That's why I said a while ago, make sure that you copy the original code and then you rename the one so that way in case if you mess it up, you always go back to the original. Right, that's what she was asking. It's just a test. Just test. Yeah. So maybe you want to run that main program. So there are two, one for two examples. You run it and see if it matches with your result, and then what you do is you go through the MATLAB code and see what each of those portions are doing. To understand. You see what I'm saying? Yeah. First run it without as it is. And then what you do is you put some commands in between and see what changes. Yeah. So have you run that one? Yeah, it's working, right? So run it, let's see what it has. Let's not just so you know. So he's showing the states after working. So now what you can do, yeah. So what you can do is you can actually now go back and the code and see why is it 1 to 1. Like you can put some commands in between. The ones that you are aware of, you see at what values are its change. You know? Right. These are regulation might, maybe, why don't you hold that question? Let us first cover this. Then we'll talk about it. Basically, what you have to do is, I mentioned tracking is a little more easy to problem because you have to have two laws. In regulation, you're only using the feedback. That's u star equal to minus half r inverse, right? In tracking, there's an additional term you have. That term is a function of the trajectory. The one that's like what you were saying, the trajectory that you were saying. Yeah, that's it. That is right. So what happened is we have to find that term. Sometimes that term is a function of the dynamics. So the dynamics is not known. So what we normally do is you have to create another argumentative system. So the trajectory has to be created in a way, and then you take the argumentative system as the error dynamics between the state and the desired value, and then you put another one which is the trajectory as part of it. Okay? So function of time as part of that design. Yeah. Right. But you see, it's not just the trajectory dynamics you are talking. It is how that is playing when you remember I said two terms, right? The term that goes pre-border now that brings in, even though it's tracking, it brings in the dynamics of the system also. That's why the system dynamics are on. It's not just the trajectory dynamics, it's also a function of the, so there are two terms for tracking. One term for regulation, which is what you are doing. You're tracking what you are doing is you're mapping the tracking problem into regulation. And that's where we create that augmented system. So maybe what I will do is one of those times, I will bring up some example and then I will show you how to rewrite this code. But none of the codes is given to you for tracking. We are not covering tracking in this course. But what you can do is I will give you a suggestion for a paper. Maybe I'll talk about it. Then you can, and then you convert it. It's not that hard. So you're mapping a tracking problem into a regulation law by doing the documentation. That's all we need to do. That step, once you do it, everything will work. You see what I'm saying? And you vary, like you said, you can vary the state of charge, what is the desired profile, any way you want it. It doesn't have to be a constant value. You can say after some time I'm changing like this or this. So we are not covering because we have covered quite a bit on the regulation. Now let's do the regulation before we get into tracking because that's a little more difficult. Remember I said that. That's why you get an additional term in there. And you need to know how you derive that additional term. We haven't talked about it, unfortunately. Okay? And so we will do that at the end of it. So hang in there. So that's intro to all works.
Yeah.
I told them, they need to learn the coding like MATLAB code. They need to understand it, So let me call your attention. Remember, the MATLAB code, this is not produced for commercial purpose. You probably know, right? So it's not mainly a code that was commented out, like things like that, so that somebody can use it. So this is basically to help you, to assist you. That's all I would say that. So you need to be patient when you are going through the code. Make sure that one way to learn from the code is primarily you can put some commands in between. Say, okay, I want to print some values as the code is running. So you can do that. So this way you understand what that portion of the code is doing that Sir was telling you. Remember, okay, this portion is doing this portion is doing that. So that's what you guys have to do, unfortunately, because even any book you take, you would not be able to, when you go through the code, because people write with different styles. Remember, that's what we were talking about. People write in different styles. So this style was mainly everything is mapped into subroutines, like different. So they are being called into the main program. You see? And so this is the way it was written. So different people write it in different ways. Some people put everything in the same program. Some people write it because the benefit is, I'll tell you, is you can change the system. You don't have to change the main program. You change and then you can call this. So you can, see, that makes it easier. The other thing is the controller. Let's say you have a system. Now let's say I want to have a different controller. I want to, I want to run. It's easier because you have a system. You call the same system routine into a different code for the controller. So this is why everything is typically modularized. Okay? So there are two ways you learn. One is make sure you get the commands, put some commands inside, and you run it and learn or understand what that code is doing. You see? The main thing is you have to make sure it works. The versions match and all that. Once you get that, then you can do all these things and then you learn from it. Then, no, that's one thing. Second is, remember, unless you do that, you can't make changes like what we are discussing. Let's say if I want to do tracking, what changes do I make? You won't be able to understand. So this is what I suggest you to. Okay, so spend some time. Be patient with it because at least it's working. And don't overwrite the code because then it's a problem if you make a mistake. So make sure you save the original stuff somewhere and you copy it into some name and then you play with it. Because I have done many times some changes and something blows up and you don't know what changes you made. It's like learning where you're playing with those kind of things and suddenly it blows up and you won't know what causing this blow up, right? So keep that in mind, okay?
Okay, do it. I will stop here and maybe